to do under the assumptions that we had. Let's simply try it out on our example to see if it really works. So for our example, we had, initially we had a domain of natural numbers, but this is an infinite domain, so we cannot use it really. So here we will just use the domain of integers from 0 to 10 and our same function from before. And now we would like to find a fixed point by simply executing this algorithm, which is easy. We start with x is the smallest element in our domain, which is 0. Smallest, yeah, for integers this has some natural meaning anyway. I will also number the different versions of x. What our algorithm now does is it computes a new x by applying f on the old x. So basically, in our first iteration, we compute f of 0, which is 0 plus 10 divided by 2, which is roughly 5. So this is our new value for x after the first iteration. Now we check whether x changed. X changed from 0 to 5, so we are not done yet. We have to continue. So the next value of x is computed again by applying f to the old value of x, which means we compute f of 5, which means we compute 5 plus 10 divided by 2, which is 15, is roughly 7, right? Again, we check whether x changed from this iteration, from the previous iteration to the current iteration. Yes, it changed from 5 to 7, so we continue with yet another iteration where we again apply f now to 7, which makes 7 plus 10 divided by 2 is 17, is only 8. Again it changed, so we have to continue. So I see this is not really an ideal example because it requires a lot of writing. But now we should slowly converge. We have now 8 plus 10 divided by 2, which is 18 divided by 2 is 9. Yet again, x changed, so we need yet another iteration. And now I just write 9 plus 10 divided by 2, and this is again 9. We already had this before. So now x did not change in this last iteration anymore, so our algorithm just terminates, and the final result is the value 9, which is indeed the smallest fixed point of this function. Basically, what we could do is continue here also, computing x6, x7, x8, and so on. But what would we get? We would always get 9. Because by applying f to x, we always get the same value again. So we could continue, but it doesn't make any sense because the value doesn't change anymore. So we can as well quit. This is the basic idea of the algorithm, actually. Conceptually, we should continue, but nothing changes anymore, so we can also stop. We are done. Okay, so for this simple example, our algorithm worked, but actually, initially we wanted to solve a completely different problem. We were talking about least fixed points in mu calculus formulas. Mu calculus formulas are formulas over sets of states. Now that we know what a fixed point is, conceptually, let's now see what this means in our mu calculus formulas. The form, the syntax of a mu calculus formula, including a least fixed point operator, is always like this. We have the letter mu to indicate that this is a least fixed point. Then we have some variable x, and then we have a mu calculus formula where this variable x appears. Now, we already said that mu calculus formulas always evaluate to a certain set of states. So the result of evaluating this formula is always a set of states. And also this variable that we have here is a set of states. So actually, this formula phi here can be seen as a function which takes as argument a set of states x, and it also produces as a result a set of states. So just as we had functions here, here our functions took an integer and produced an integer as a result. Here we have functions, actually Mu calculus formulas, which take as input a set of states and produce as a result a set of states. But still the idea is basically the same. So the meaning of this least fixed point operator is now it should be the smallest set of states such that phi applied to x is again x. And again, we can reuse the same algorithm from before. So before the algorithm said start with the smallest element in your domain. Now our domain is sets of states. So the smallest set of states is clearly the empty set of states. And while our set of states x changes, we compute the new set of states x by evaluating our formula phi on the old set of states x. And this we repeat until nothing changes anymore, and then naturally we will obtain a fixed point for this formula. Again, this algorithm we can only apply if our two assumptions are satisfied. Remember that the two assumptions were our domain needs to be finite. Now our domain is sets of states, but in our game graphs we always just have a finite set of states. So there are also just finite different subsets of all states in our game graph. So the domain is finite, this is fine. And the other assumption is that our function that we apply to sets of states needs to be monotonic. Previously I wrote this with a less or equal sign, but in the domain of sets of states, this naturally translates to a subset relation. So basically what monotonicity here in this context means is if we put in a smaller set into our formula phi, then what we will get will also be a smaller set. Or the other way around, if we put in a larger set y, then into the formula phi, then the result will also be larger, it cannot be smaller. So this is an assumption that we have to check before we would like to apply this algorithm to compute the meaning of a fixed point operator. So there are two different ways of thinking about such least fixed point formulas or fixed point formulas. You could say, well, it's a formula that describes a certain set of states. But you could also say, well, actually, this is just a very short way of writing down this algorithm. Basically, whenever you see such a fixed point formula, you do not have to think a lot what it actually means. What you have to do is, you can always use this algorithm to compute what this fixed point actually means. You can use this algorithm always to compute the result of this fixed point formula. Let's try to do this on an example. This is the same game graph from before, and in order to make this easier for you, I also printed you handouts where you can also find this example so that you have it next to you while we go through it. So our task is as follows. We are given this game graph, and what we would like to do is we would like to evaluate this Mu calculus formula here. The meaning of this Mu calculus formula is always just a certain set of states, and we would like to compute this set of states that is described by this formula here. This formula contains a least fixed point operator, so in a way we will use our algorithm from before to compute the meaning of this least fixed point operator. It also contains a fixed set S, which contains only the states 4 and 6, and it also contains a function. which takes as argument a set of states, and it produces as a result a set of states. The function that we have here is the set of successor states in this graph. This is quite intuitive and here also defined formally. So our goal is now to compute what this Lie calculus formula actually means, and we do this usually in the following way. When we see such a fixed point operator, then we simply write down our algorithm to compute the meaning of this fixed point operator, and recall that our algorithm works in the following way. We start with the empty set of states, and then while x changes with the new value of x is our formula phi evaluated with the old value of x. And now our formula phi is defined like this. The phi part is S union successor of x. So what we need to compute basically is the result that would be produced by executing this algorithm. So there is not really a lot of magic to these Lie calculus formulas. They look complicated, but whenever you see one, what you do is you just write down the algorithm to evaluate it, and then you can just execute the algorithm in your head. And this is what we will do now on the blackboard, and then later we will also solve a similar example, and I would like then you to do it on your own, so that you also get the feeling yourself. Okay, so now let's now just execute this algorithm to compute its meaning. So we start with x is the empty set of states, and as before I just give all the x's an index to distinguish them from each other. So our algorithm, the first time we always enter this loop, because this exchanges have no real meaning before we executed the body of the loop at least once. So initially we always enter the loop and we compute the new value of x by applying our formula phi to the old value of x, which basically means that we take our set of states S, and so this should be an x, otherwise this doesn't make any sense. Take the union with the successors of x. So this means our set S is defined by being the states Q4 and Q6. Q4 and Q6. And here we have to take the union of the successors of the empty set of states. And the successors of the empty set of states is basically just the empty set of states, because no state has no successor. So basically this is just Q4 and Q7 as a result of executing the first iteration in this algorithm. So this is now our new value for the variable x1. Now we continue to execute this algorithm. What we need to check is whether our set of states x changed. And it did change, because before it was the empty set and now it's the set of states 4 and 7. So it changed, so we have to continue doing another iteration. Yes?
Shouldn't it be 4 and 6?
Yes. I should actually have printed out a solution to always cross-check, but I have you also, luckily. Okay. So we need to do another iteration, which means we need to evaluate our Lie calculus formula phi once more, but now with the new value for x, which works in the same way as before. Phi is defined to be this formula applied to our old value. S is as we had it before, namely Q4 and Q6. Union the successors of the set of states Q4 and Q6. This part is easy. Q4, Q6. Now, more difficult part. What is the set of successors of 4 and 6?
5.
Sorry?
Q5.
4 and 6 is only Q5. Let's write it down and then think of it. Yes, Q5 is the only successor of either 4 or 6, because the only successor of 4 is 5 and the only successor of 6 is 5. So this is the set of successors of these two states contains only this state. So as a result, we obtain here Q4, Q5, Q6. This was the next iteration. Again, we check whether the value of x changed, and it did change from 4,6 to 4,5,6. So unfortunately, we have to do another iteration. Again, evaluate phi with the most recent value for x, which is again s and the successors of x2, which is Q4, Q6 union the successors of x2. x2 is Q4, Q5, Q6. Q4, Q6 union. Now the difficult question is again, what is the set of successors of the states 4, 5, or 6?
4, 5, 6.
Let's think of it. So 5 is definitely in there because it's a successor of 4. 6 is
4.
Yeah. 6 is also in there because it's a successor of 5. 4 is not really in there because it's neither a successor of 4, nor 5, nor 6, so it's only these two. So we have 5 and 6, Q5 and Q6, and when we build the union of these two, then we get Q4, Q5, and Q6. Yet another iteration of our algorithm done. Again, we check whether x has changed. The previous x was 4, 5, 6. The new x is also 4, 5, 6. So this means our algorithm says we are done. And the final solution is basically the meaning of x s and successors of x is Q4, Q5, Q6. Perfect. So this is how you solve Mu calculus formulas containing such a least fixed point operator. You do not really have to write everything down. You can also find all the solutions on the slides. That's also the reason why I did not yet upload the slides. But I will do this right after the lecture. Okay. There is one more thing to Mu calculus formulas. We are almost done. There is not only a least fixed point operator, but also a greatest fixed point operator. But it's almost the same thing as before. The only thing that changes is that a greatest fixed point operator is always written with a mu instead of a mu. But the rest looks exactly the same. We all again have a variable which represents a certain set of states. and a mu-calculus formula which takes a certain set of states as argument and produces a certain set of states as a result. The algorithm to compute a greatest fixed point changes slightly. Previously, we started with the smallest possible element and had elements getting larger and larger and larger until we hit the fixed point. Now, we start with the largest possible elements, and the elements are getting smaller and smaller and smaller until we hit the fixed point. But essentially, the algorithm, other than that, stays exactly the same. And also our assumptions basically stay the same. Again, the domain needs to be finite, and again, this function phi needs to be monotonic. What I would like you to do now is to practice this a little bit, solve a very similar example to what we have done before. It's exactly the same game graph, exactly the same function that we use, namely the function that computes the successors of a certain set of states. Now I would like you to evaluate this mu-calculus formula here, which contains a greatest fixed point instead of a least fixed point.